Good morning, everyone. Thanks for coming, and let's see whether we can make a lively presentation discussion for this morning. So briefly, I would like to repeat where we have ended yesterday. So one of the most important aspects that we have discussed in the lecture about thermometry was so far that we can measure temperatures by using the Boltzmann equation. And the Boltzmann distribution function is, just to repeat that, the fractional population of molecules in a certain eigenstate I, which is given by the degeneracy factor times the exponential here over the eigenenergy over kT and over the partition sum, summed up over all possible states. And so the idea was to measure this quantity here and those two quantities here taken from quantum mechanics. And with that, well, we have the opportunity to combine spectroscopy with quantum mechanics and thereby resolve for the temperature, for the thermodynamic temperature given here, without any calibration needed. Yeah, that is the most, or the best suited way to do it, because calibration always is a problem. And when we discussed that, well, the idea was to see whether or which technique might be best suited to do so. And so we have gone through different techniques, and those techniques have been absorption spectroscopy. And absorption spectroscopy is a nice tool. However, the problem is that we don't have any spatial resolution along the laser line. And so let's call that limited spatial resolution, because perpendicular to the laser direction we do have spatial resolution. Then we have looked into laser-induced fluorescence. That's as well a great technique, and it provides the opportunity to spatially resolve what we want to measure and have small probe volumes. The problem here was electronic quenching, energy transfer that is not due to emission and that is very difficult to quantify in the end. And for thermometry, we have seen, if you do two-line thermometry, for example, that you can, in some cases, the effective lifetimes associated with that cancel, but that's not generally true. Then we have looked into Raman spectroscopy. And Raman spectroscopy, just to remember, was the effect when we have a laser which is non-resonant with the any allowed transition, and you have an inelastic scattering process such that after the process, the system is in a higher or lower quantum state. This would have been here the Stokes shift, where we end up in a higher quantum state. And if you do that from different levels, of course, you would as well get access to this number densities, this fractional population. The problem with Raman scattering actually is that you have extremely low cross-sections, Raman cross-sections. And so you have to overcome that somehow, and that means you have to have a sufficient number of photons, high energy, although you need as well very sensitive detecting units, yeah, to get as many photons that are created, as many Raman photons as possible. Okay? And so I would like to continue that now with the last technique that is referring to the Boltzmann distribution function, which is now a nonlinear technique that needs as well a bit more explanation I guess. And so I will try to explain that in the following way. Once again, you do have your diatomic molecule, which is surrounded by electrons, and we make this very schematic, okay? You have here something like that. This is a very crude model of your molecule. If you now have an electrical magnetic field, and we just look for the electric component for the moment, then that comes from your laser, then what it does, you create a force acting in such a way that the electrons are pulled against the nuclei. And so what you create is a polarization. And this polarization can be expressed here, pi, if you refer only to a linear response. That would be like in Raman, in spontaneous Raman scattering that we have discussed so far. You have a direct proportionality. And what is in between here, that is a molecule-specific quantity. This chi tensor here, the the difficult word in English, susceptibility of nth order, that actually, you have an idea, is that a scalar or is that a tensor of second rank? It must be a tensor of second rank because this is a tensor first rank, a vector, this as well. So here you do have, in general, 9 components, right? And only if you have an isotropic molecule, it's a scalar. Yeah. Then you would have, that would mean if you have a scalar, then it would be an equal polarization if you pull the electron in this direction, or this direction. But this is generally not true. That's why you have to have here a tensor notation. Okay, this is up to here. This is the linear world. And if you don't have any lasers, you stop here. However, in the case of lasers, where you have very strong electrical fields, you have higher orders, like second and third order. And, well, you can easily show for gases, because of symmetry reasons, I don't go into detail, that chi2 here is always 0, whereas then the lowest nonlinear order in gases is the K3 term. It's a third order term. And, well, it's interesting to note, if you now look for these molecular specific quantities, these K tensors, K1, K2, K3, the differences are significant. There are many of order of magnitudes in between. And because of that, we can expand that into this expression, otherwise you couldn't. And that as well makes the normal world linear because of these higher order terms are so small. So you have to overcome their small value by having extremely large electrical fields. And that means you have to have lasers. And that's the unique thing about lasers, that you can get this nonlinear effects. And this is now exploited in car spectroscopy. Yeah? So the basic idea is now you have this disturbing electric field, and now your molecule is reacting not in a linear way, but in a nonlinear way. The response function is nonlinear. Once you have this polarization term, yeah, in a semi-classical way, you can put that now into the wave equation coming from Maxwell's equation to the left-hand side. You put it in here, and if you resolve this equation now this is something like a source term. This gives rise to a new beam containing the signal, the car signal that we are going to talk about. And actually in this term here, here's the fractional population embedded. Yeah? So the temperature information is already contained in this polarization term. And this is now the source term used to calculate the signal intensity. And when you go through this more or less complicated mathematics, you find that you create a fourth beam, because as you will see in a minute, we will shine in 3 laser beams that are nonlinearly interacting, giving rise to a new beam which is coherent, which contains the information about the fractional population, about the temperature, and does have a term that is not existent in linear spectroscopy. And this term we have to explain a bit more in a second. This is called the phase matching that has to be fulfilled. If you go now from the electrical field to an intensity, that is typically what you measure, you have to take the square of that. And if you do that, you find that the chaos intensity is now non-linearly dependent on exciting lasers. If you refer back to spontaneous Raman, to absorption, to fluorescence, all of those had a proportionality where at the right-hand side the exponent was 1. Now you see you have here squared and here to the power of 1. So in total it's the power of 3. Yeah? And that is now why it's called nonlinear spectroscopy. It depends nonlinearly on the exciting lasers. And again, in this expression, you find here this K3 term that is containing, as I've said now many times, the temperature information. This is the interaction length of 3 lasers. So that goes in as well, which means the intensity will be smaller. The smaller the probe volume is. Again, that's the devil of diagnostics in spectroscopy. You want to have a higher resolution in space and you get less signal. Yeah, that's a penalty always. And this is this phase mismatching term we need to explain a bit more in detail. After that brief theoretical background, now a pictorial view of what CARS actually is. What you do is you have 3 lasers, and in practice you take typically 2 green lasers, frequency double YAG lasers, pulsed, 8 nanoseconds or so, and you have here a dye laser with omega 2. And so let's maybe start only with the first 2 lasers. So you have here omega 1 and acting with that simultaneously omega 2 in a nonlinear way over this virtual state. This is like Raman. Yeah? If you would have only omega 1, that would be like Raman excitation. But now you shine in with a high intensity simultaneously omega 2. And that means you have a 2-photon difference frequency process. You bring it up, and you bring the molecule directly down, and if this difference, omega 1 minus omega 2, matches an Raman allowed resonance, omega r, and it brings it back to this eigenstate, which is a different one than you would start it with. If you have a mismatch where omega 1 minus omega 2 is not hitting an allowed eigenstate, this is again shown by this dashed line. This is a very improbable process that then continues. So you have to fulfill this to have a Raman resonance to have CARS signal. Okay, let's go on now. Maybe one more word. If you, this photon, this omega 1 photon, is destroyed afterwards. That's gone. But this photon, omega 2, because energy has to be conserved, so after that process, you have 2 omega 2 photons. Yeah, this is something like you bring in this energy of omega 1 is brought into an additional omega 2 photon plus this higher energy level in the molecule. Yeah? So just to make sure that the energy balance is fulfilled. Then, very often you can, typically it's done in normal cars, that you then directly, simultaneously have another omega 1 photon. You bring it up to this state, and then because of this equation I've shown beforehand, because of that one here, you create an omega 3 photon, which is now your signal. And this is a so-called parametric process now, because you start at this level and you end at this level. Hereby, you have no energy deposited in the molecule, right? So you're really non-intrusive. And this omega 3 photon, that contains now the fractional population from Boltzmann, the temperature information. You have to fulfill some selection rules, so you cannot combine omega 1 and omega 2 arbitrarily. You have to fulfill that the J levels is changing either by 0 or plus minus 1, and the vibration level as well by plus 1. And so that is something maybe you have seen already sometimes, or some people. It's maybe less intuitive to understand the phase matching. So this is just to confirm that the energy balance is fulfilled, right? Now, in the phase matching, you have to make sure actively, in this sense, in this spectroscopy, you have actively make sure that the momentum balance is fulfilled, yeah? And the momentum balance is expressed by this K vectors. If you go, again, into quantum mechanics, you find that the K vector is directly proportional to the momentum. Yeah, this is maybe we can switch that on for a second again. You can show that the momentum of a photon, or as well as of particles, is directly proportional to the wave vector. And this is here the reduced Planck's constant. And with that, it maybe becomes more clear. If you have 2 photons, these 2 omega 1 photons, which are destroyed, they're not existent anymore, their momentum must go somewhere. And I said already that the omega 2 photon will be doubled. It will be created a new one. So this momentum is going into the new K2 photon, the new omega 2 photon, and the remaining must go into your signal photon, which is now here denoted as K3. And so you can now try to fulfill this momentum balance in such a way that you have, for example, a parallel beam arrangement. K1 plus K1 must be K2 plus K3, all of them pointing in the same direction. If you would do so, the problem would be you would have no spatial resolution because all these beams would be on top of each other. So that's something we don't want. That's why we take it differently. We now have these two omega-1 photons with the corresponding K1 vectors, and they're in a certain angle, like that. Yeah, you select that, and thereby you have a crossing like an LDV, a certain overlap, and only in the overlap you have the signal created. Then you take the K2 or omega-2 photon, and you arrange it now with an angle such that the produced K3 photon, omega-3 photon, with its wave vector having a certain length, yeah, because that's fixed, yeah, is balancing the remaining momentum. And that means you actively have to control the directions of your three laser beams to make this happen, to fulfill that this expression is going to 1, right? That is what you have to do. And you might ask the question, why don't you have to do that in, for example, laser-induced fluorescence? Well, in laser-induced fluorescence, what you do is actually the momentum balance is fulfilled. But if a photon is going into some direction, the molecule will move in a different direction. You put on momentum as well to the molecule, which means you add momentum plus energy, you deposit as well energy into this molecule, which might dissipate afterwards. But as well, you add momentum to that molecule. And that is something which makes it, in principle, non-intrusive, makes LIF intrusive, although the amount of momentum you add, the amount of energy you add is very small. Yeah? But you have to just be aware of that. Okay, and so that comes now to the point where people now think of arrangements like that one here. You have here the two green beams from one YAG laser. You have here the dye laser, and they are arranged not arbitrarily, but they are arranged in such a way that you fulfill the phase matching, the momentum balance, and then you create in one direction your signal beam. And this signal beam now, if you do it in that way, for example, is not overlaid to the other beams. It is separated. Yeah? It does have a different wavelength, and it is coherent. And that is one of the big advantages as well. So you don't have to place your detector very close to the combustor, but you could put it 10 meters away. All you have to put close is here this collecting lens to make sure that you have this lens in the focal distance of this probe volume over here to make a parallel beam out of that. But once you have that parallel beam, you can guide it over many, many meters. And that means you can place your spectrometer and the camera even in different rooms. And that is, in big combustors, a clear benefit. So that's important. You got the message? Otherwise, please ask. Yes, please.
The omega-1 and the pump and the probe, if they are not of the same wavelength, this is a degenerate car.
In this cars, this is the low vibrational cars. There it's different. There it's different. We will.
Still be satisfying the momentum balance criteria, because it's just a vector map, and you can always have different strengths, and you can still match the cars momentum balance criteria. But will it affect the selection criteria for the Raman resistance? If you have different pump and probe.
If you have only pump and probe.
No, you have different wavelengths of the pump and the probe.
Yes.
Will it affect the Raman resonance?
Will it affect the Raman resonance? Well, not sure whether I completely understand your question. However, if you have these two wavelengths or frequencies, they have to fulfill, first of all, the selection rule. Otherwise, it will not happen.
No,
that is given.
You have this as 532.
This is 532, and maybe this is N2, and then you would have here something around 607. Yes.
If the second probe,
That one.
yes, if that is different from 532.
Okay, no problem. No problem, you can do that, but then you need a third laser. Yeah, it's just a question of money, and you can do that, no problem. Yeah, people have done that with 3-color cars. Yeah. Okay, sorry for being slow in understanding what you want. Okay, so you have 2 ways to do cars. One is scanning cars. So you typically have a fixed pump laser, 532 nanometers. YAG lasers cannot be tuned. And you have one dye laser, and this dye laser is now tuned in time, and then you look for these Raman resonances that then give rise to this car spectrum. That needs scanning needs time, turbulence doesn't give you time, forget it. That's why you have to do it differently. In turbulent combustion, you have a broadband dye laser. A broadband dye laser gives all the frequencies simultaneously that you obtain here time after time. And so these Raman coherences between the pump and the omega-2 photon give rise now to an instantaneous spectrum. So the Car's beam contains the full spectrum at once, which means before you detect it, you have to spectrally separate that. And this spectral separation needs a spectrometer. And that's the bad news. The spectrometer needs high resolution in the order to resolve these single lines, and that means typically you have to use a 1-meter spectrometer and a grading with 2,400 lines per millimeter. But if you do so, now we are after the spectral dispersion. You have now here your spectrum, and I have here calculated for you 3 temperatures, 300 Kelvin, 1200, and 2400 Kelvin. And this is raw vibrational cars of nitrogen, and nitrogen typically is used because it's a well-known molecule, it's a relatively simple molecule, and it's existent in all combustion processes. Of course, if you do oxyflame combustion, you have to do something different. If you have 300 Kelvin, you find this kind of spectrum, which is very narrow. All the rotational lines are so close to each other, and only a few of them are or populated. So at 300 Kelvin, it's not very useful compared to higher temperatures, and that is as well the main strength of raw vibrational Raman of N2 is at high temperatures, maybe starting from 400 Kelvin or something like that. And there you see 1200 Kelvin, 2400 Kelvin, the full spectrum, yeah? And it's really different from each other, that you can very precisely measure that. And maybe it's nice to see as well, now nice spectroscopy from the point of view that you have here the Raman resonances from the lowest vibrational state to the first vibrational state, that is in this region, from the first hot band, from the first vibrational to the second vibrational state here, and this is the second hot band from 2 to 3. Yeah? Okay? And that happens as you see, this higher levels, these higher vibration levels are only populated at high temperatures, as I said yesterday. Yeah? Okay. And now we can measure those spectra. We can either, one way, of course, is to fit now theoretical spectra to this measured spectra, and that's the way typically it's done. Yeah, we will see some examples in the following. Or, of course, you can as well select now single lines here and make ratios out of them to get the temperature based on Boltzmann distribution. But this is typically not done because you can simulate those spectra quite nicely. You can fit them by changing the temperature, looking for the best match, and thereby select the temperature. And if you have very good lasers, which are very frequency stabilized, like injection seeded YAG lasers and stable broadband dye lasers, you can obtain something like a precision of better than 2%. Yeah? A precision of better than 2% means at 2000 Kelvin, you have it in the order of, let's say, 40 Kelvin or better. Yeah? I think the best I've seen was reported in the order of 20 Kelvin at 2000, which means you have a 1% precision. And you're accurate, because you refer back to the Boltzmann distribution. And that is something you cannot do by any other technique. You have no other option to get that precision and accuracy. And here you see single shots. Yes?
Why we are seeing so many fluctuations instead of just one for every band?
The fluctuations here?
Like in the
Yeah, this is due to the fact these are the different rotational lines. I'm not sure what you mean by fluctuation. The fluctuation is those peaks here. Yeah, these are the different rotational lines. You go from the first vibration to the first, from zero vibration to the first vibration state, maybe here, yeah? But you start not only from one rotation level, but from the different rotation levels. Maybe I should make a drawing again, because that is important. Otherwise, it is not clear yet. Maybe I draw only the first band. So this is the starting point, and this is where you end in this first band. And here you have different rotation levels. This is not, maybe I take only those, and you end in those. And maybe we now take an example, delta J equals 0. That's only one option, but the most intense one, that is called the Q branch. Yeah? And now we maybe go from here down to here. We go, and I make now a second one. We go from here down to here. Okay, I've now only drawn two of them, and those have been maybe this one and this one. Yeah, okay. So these are the different rotational vibration levels from which you start, and fulfilling these selection rules, giving rise to this spectral shape. Okay. Okay. And you really see that. These are single shots in room temperature up to 2140 Kelvin. And you see now that there is, it's difficult to see, but it's actually two lines, black and red. And black is measured, red is simulated, and the residual is the blue line over here. So the FIT tries to make this residual as small as possible, and that can be clearly seen whether you have a good measurement or not. If the residual is flat over the whole spectral range, you're fine. Yeah? And that is maybe the most powerful technique that we have to measure temperatures. And that is takes some effort, and maybe in the later this morning, I will show you how we combine that with fluorescence measurements, for example, to measure CO. It is not a cheap technique, because you need a well-behaved YAG laser, you need a dye laser, you need a lot of optics, you need a spectrometer, and you need a CCD camera to measure that. So in total, I don't know, maybe 400,000 euro or something you have to invest. And even though you have that, you need some experience to make it happen, to get good signals. Okay? All right. Let's have a close look into the pros and cons. It is precise. It is capable to do single shot in the gas phase. The coherent signals allows you to have the detector placed far away and no calibration required. The disadvantage is complicated setup. If you have beam steering, if you have optical excesses and so on, things can be nasty, but it's doable. People have done that, we as well, in combustors. The spatial resolution in beam direction is not so good, because if you look at these intersecting beams, you have these focal areas like this. I try to draw that like this. I draw only two beams, okay? Then you have, in this direction, you can go as low as maybe 50 microns. But in this direction here, in this overlap region, you might be in the order of 0.5 millimeter or worse. However, those limitations in spatial resolution have been overcome by very recent approaches from Chris Cleaver and Sandy National Labs, and maybe I have some time later on to show you these recent developments where he was obtaining, even in this bad direction, something like 60 microns. Yeah? This is a different car setup, and maybe I have time to explain that. And as well, typically where it came from, cars was a point-wise technique. However, this new developments show you can go to 1D and even 2D Karos measurements. But that are not based on nanoseconds laser anymore. That are based on femtosecond and picosecond lasers. Yeah? So even, let's say, more complicated laser setups. Okay. Any questions? Yes, please. Yes. That's correct.
Yeah. How important are those things? Can you compromise on the resolution?
Yeah, well, you can compromise, of course, but then you compromise typically as well on your precision. Yeah, so there's no free lunch. You can do that, but you have to test out. You know, you have to check it. Then you take your, I don't know, calibration flame where you know that you don't have any heat losses. Take a flat flame, for example, and be sure that it's adiabatic or as adiabatic as possible. Yeah, and then you repeat your measurements 1,000 times. You take the standard deviation. You'll see your precision. Yeah, in the single shots. But I think you will lose precision. All right. Then let's continue. After we have spent so much time into these Boltzmann fractions, you should never forget that now, even if you're working in the numerical part. Let's have a look now, a brief look into temperature-dependent absorption emission spectra. Well, here, the idea is a very different one. Here, you typically add traces to your gas and perform fluorescence measurements only. Only back now to fluorescence. And typical traces are aromats, ketones, or aldehydes, in some cases even atoms. However, that has been attained attention over the last 20, 25 years, and people have looked into different hydrocarbons that are suitable as traces. But of course, if you put a hydrocarbon into that, it will not survive the flame. So we're talking about a measurement technique for temperatures ahead of the flame front. Very often that is required in IC engine combustion, for example. That is very important. However, atoms, they have, like indium, those atoms, if they are put like indium chloride into your fuel, they are produced only in the flame front. And so those atoms are capable of measuring temperatures only in the exhaust gas. And so you see, this is already not the best choice because you have more restrictions than before. Okay, well, there are some benefits. You can choose your tracer and its spectroscopic properties according to your measuring task, but there are many disadvantages. Hydrocarbon traces decompose typically around 700 K. Only up to this temperature you can do that. And so for IC engines looking for compression temperatures, that's very important to look for auto ignition, for example, HDCI combustion and things like that. However, traces may influence the physical properties of the fluid. They can as well maybe promote auto ignition if you have bad luck, so you have to be careful about that. And well, very often, for most of the traces, they are not independent of the surrounding gas phase. Yeah? So some traces are good, for example, only you have a nitrogen atmosphere. That might be a drawback. So those, I'm not a chemist, however, here are some structural formulas of the ketones. Acetone and 3-pentanone have been used regularly. Aromats, toluene, that's as well others. Acetaldehyde has been used, and you see this list is far from being complete, and people are doing research on that, finding even better traces. However, some of them, like toluene, although it's very often used for thermometry, it is very sensitive to any O2 contains, and you have O2 toluene collisions after you have excited the toluene. The excited energy is quenched by the collision with oxygen. So oxygen quenching can be a showstopper. Yeah. Okay. So there are different options. One option is you have a two-line excitation, meaning two lasers, and you have one color detection, which means that you have as well two detectors, and they are not measuring simultaneously. One laser and one camera fired, and then maybe a few hundred nanoseconds later, the second one. And therefore, you exploit the temperature-dependent absorption band. But here, you have, again, a number of practical issues. Bringing two lasers on top of each other is not easy. Yeah? They have two different wavelengths, and you have to make sure they match each other as perfect as possible, having the same thickness in the sheet and so on. And so practical problems might be as well here something that limits yourself. And so by principle, a single line excitation is smarter. Yeah? And here you have only one laser, but you have a two-color detection, meaning that you exploit the temperature-dependent emission. Yeah? And that is something I will exemplify in the following in more detail. However, let's start with 3-pentanone LIF. which is an example for two-line, one-color thermometry. And that has been published, I think, 1906 or something like that from the Wolfram Group in Heidelberg, where you see here the normalized absorption spectrum of the 3-pentanone molecule for different temperatures. This is shown here in 373 Kelvin in black up to 523 Kelvin in blue. And you see the spectrum, the absorption spectrum shifts. You could measure, of course, either the whole absorption spectrum, that cannot be done in turbulent conditions. So that's why you use fixed wavelengths. You typically take wavelengths that are available, like X-hammer wavelengths, 248 or 308 nanometers from krypton fluoride or xenon chloride lasers, or you use 266 nanometers, which is not shown. 276 can be generated easily if you shine a 248 laser into a hydrogen atmosphere. You take a cell, 10 bar hydrogen, and then you create stimulated Raman scattering. Creating 276 nanometers is here something which is easily possible. However, if you now take the signals taken at two different excitations shown here, the signal at 1 and the second wavelength, and you divide them by each other, you can show that the absorption cross-sections, the ratios of them, and the quantum yields, meaning how many photons are actually coming out of the excited band, are a unique function of temperature. Yeah? That is possible, and that has been demonstrated with the complexity that you have to overlay these two lasers as good as possible. For more information, either I refer to this textbook. However, I gave to Satya Chakravarti as well some lecture notes I have written where you find all the references in as well. The other way is, as I said, single line but two-color thermometry, where toluene is a good example. What you see here to the left-hand side is now after excitation in the UV. Maybe you have now a 266 nanometer laser, a fourth harmonic of a yak, and you look at the normalized fluorescence spectra. You see here for different temperatures, for rising temperature, a red shift. So the spectrum is shifting with temperature to higher wavelengths. However, be careful, the spectra are normalized. And that means what I hide here is the fact that for higher temperatures, your signal decreases enormously. Yeah? And that means your signal to noise for the higher temperatures is much worse than for the lower temperatures. And the second thing is, however, maybe back to the first one, you see that although they are normalized, you see that the signal is weaker. You see all these wrinkles here. That is noise. Yeah? Yeah? And in the low temperature, everything is smooth. It's a higher signal intensity. If you go to non-nitrogen atmospheres, you do that maybe in air, then you end up with O2 quenching, and then you're at least 1.5 orders of magnitude even lower in the signal, and that as well limits your precision. For more information, I refer here to a paper we have published last year about Toluene LIF. I would like, for good reasons, show its application here briefly and maybe later on in more detail, but to demonstrate how this is done, well, I refer back to the engine I was discussing 2 days ago, where you can send a laser through the piston against the cylinder head and maybe concentrate here on a certain field of view below the exhaust valves, and have here then the opportunity to measure the fluorescence coming out of this area. And this is shown here. This is the excitation plane. Now you look from the top, and what you see here are two cameras, intensified cameras, that are observing this fluorescence created over here. And this is done now with a red and a blue channel, and that is something I didn't discuss. One camera is looking for this spectral band, and the other one is looking for that spectral band. And then you have these two areas, which are then divided by each other. And if you have a changing temperature, you see that this red channel will increase in intensity, decoding the temperature. That has been done here simultaneously with PIV. I will not refer to that. We have done that at high speed at 6 kilohertz, such that we were able to resolve crank angles at 1,000 RPM. And so that is once again shown over here. You get something like this. This is the red image. This is the blue image. And this was a homogeneous charged engine. So toluene was all over the place, and I would say homogeneously, because The toluene has been introduced to the N2 that was going through the engine far upstream of the intake valve. And you see something like that. That is absorption. Yeah? Absorption is a problem. If you now take the ratio, you cancel out that problem because now the ratio, you see, is homogeneous again. And so the good thing about this way to do it is the independency of this approach of absorption, laser fluence, and as well mixture inhomogeneities, if you would have. They are not existent here, and that's why you can't show the benefit over here. But you don't have to take account of the absorption losses. Otherwise, that would be a problem. Measuring the absorption through a cylinder head is not easily done. Yeah. Okay. Are there any questions? Then we can maybe finalize that here before we look into some examples by looking into the third method, meaning density measurements. Yes? That is correct. For toluene, the overall signal goes down with temperature. No, we take the absolute. We take the absolute. Yeah, you have to take the absolute. Yeah.
So when you say that some crystals are being quenched by presence of oxygen,
yes.
So can that be overcome if you increase the concentration of toluene in the reaction room?
By increasing the toluene, yeah. Of course, you have a certain limit. You can do it within limits, I would say. So you have to think of good ways to bring in more toluene without condensation. Yeah? If you, for example, if you have, like in the engine, maybe you have an intake temperature, let's say of, take it easy, 300 Kelvin, okay? Then you should not have any condensation on the way where you put it in to the cylinder. And that's where you're limited to the saturation value. Yeah? And that is something we do in a following way. So thanks for the question. Bringing in toluene is not an easy task. Maybe we can go and have a look how this could be done. One possibility is you just take a bubbler. You have here your toluene. It's a liquid. Then you bring this into, this is at a certain temperature. You fix that in a bath. Yeah? This is isolated as well. You bring in your nitrogen. And here the nitrogen bubbles out, and here you collect it and bring it to the engine. And then you should be sure that afterwards the temperatures are higher to avoid any condensation. But if you do that and you have the saturation value reached, maybe you do it here for 290 Kelvin, and starting from here you have 300 Kelvin, you're fine, but then you have reached the limit. That's one limitation. The other limitation is the absorption. If you have, let's say, the possibility to bring in more toluene over the saturation value, for whatever reason, you might have so strong absorption that at this locations here, there's almost no laser energy left, and that you can't measure there. Yeah. So it's, again, the devil of diagnostics is you have to find a trade-off. You can optimize it, but there's you can improve it by that, but you have your limitations. Yeah, well, it's not the concentration of toluene, because the concentration of toluene would be here the same as there. It is the local fluorescence signal. And the local fluorescence signal depends as well on the local laser intensity. The laser comes from the bottom. As I said, it comes from here. So you have here at the bottom strong fluence, many photons. They're absorbed. Here you have a small number of photons. And so they have less signal. So no, this is not the concentration. The concentration should be homogeneous. To make here now a concentration measurement out of it, if you just would have that image, you can't do it. Because you have to know the absorption losses. If you would measure the absorption, what goes in, what goes out, then you could go in a reconstruction. If you would have all the other parameters known, you could try to if you know the laser fluence here, evaluate the concentration here. Then, because of Bayer's law and absorption, you could calculate what is the fluence over here, and then you could, with this corrected intensity of the laser, you get the concentration here. And by that, you march through that. But then you have to know exactly in which direction as well your laser is going. Yeah? If the laser is going like that, and you don't know, and you assume it's like that, you make a mistake. Okay, yes. Okay.
Are the valves also made of quartz?
No. I doubt that you can make a valve out of quartz. The laser is just hitting that and fine. If you, that is a good question. It can cause problems if you have, let's say, high laser fluences. You can drill over the time, not holes, but lines into your cylinder head. That happened. You can mark that somehow. But it needs higher laser intensities. Here, in that case, nothing was left, so no problem.
What's the range of temperature you can measure?
The range of temperature that you can measure is limited to something like 650 K,
So this can
700
be
K.
only during the motoring conditions.
Only during motoring conditions, yeah, because as well, that to have good signal to noise, you need nitrogen. You can't fire it anyhow. And if you would fire it in the flame front, the toluene would burn. Intrusively change your flame. Yes.
In case of the cars, at higher temperatures, the intensity comes down, maybe by one order.
Yeah, the intensity of the cars comes down as well. Yes, that's absolutely true.
Is it because the intensity is now spread over
Yeah.
more wider spectrum?
Good question. So one is, of course, you have now distributed, as you say, you have populated many quantum states. That's one thing. The other thing is you have a reduced density. And this is the other factor. If you go from unburned to burned, methane air, stoichiometric, let it be a factor of 7. And this goes in non-linearly. Yeah, it's going quadratic into that. In this K3 tensor, the fraction population is quadratic, it's to the square. And that means that hurts you really. And that means as well, because you have limited dynamic ranges, when you know you are cold, you put in filters. If you know you are more hot, you put out the filters. If you're in between, you have limited, again, due to the dynamic range, you might limit as well by that your precision. Good question. Yes? Roughly, 650, yeah. How can we use the data? We postpone the question and keep that. You will see how we use that for the compression and in the engine. Okay. Okay.
Is this profile form because not correcting it to
Yes.
flat field?
This is in this direction. This is due to the fact that you have a certain profile in radial direction, but you don't need to correct for that because we divide by each other. So that is the same argument that holds true in this direction holds true in this direction. Otherwise, you have to measure the instantaneous beam profile to correct for. Okay. Yes, please.
You have mentioned that it can be measured only in the motoring.
Yes.
If I am looking for a diffusion flame, and this is not will be useful for motoring, because
No.
there will be no fuel injected.
Right.
Then what is the use?
For diffusion flames, we use either Raman Rayleigh spectroscopy or karst.
Then if I use endoscope instead of spectroscopy.
Pardon me?
Endoscope.
Endoscope. You can, putting that in an endoscope in principle is possible. Yeah, putting cars in an endoscope, people have done that. I think I remember 2 papers or so. But putting that in an endoscope is not trivial because it's in the UV. Yeah, and so having UV endoscopes with good throughput and collection efficiency is not an easy task. That is something we currently work at. Yeah.
One more question is, we have measured the wavelength around 260 from 260, and if I want to just see more soot particles, then I have to go less than 200 nanometers. So is it possible in this case?
Well, in case of soot, there would be no toluene because soot will be produced only if you have had a combustion.
And for flame intensity, have you comparing any wavelength of the two different flames, or how you are measuring this flame intensity?
Measuring flame intensity, I didn't say, repeat it please.
Is it possible to measure the flame intensity?
Measure the flame intensity. You mean chemiluminescence? Yes, sure. You can, with this kind of cameras, you mean? You can, yeah, sure. You can, those cameras themselves are not UV sensitive, but with the intensifiers they are. With those devices, you, for example, can measure down to OH chemiluminescence at 308 nanometers. You can measure CH star chemiluminescence at 430. You can measure as well, without the intensifiers, the soot emission if you wish. Sure, yes. Okay. So then let's maybe finalize that with the density measurements where you exploit the equation of state, make it simple, the ideal gas law. And so once again, that can be done based on this view graph based on Rayleigh scattering. So if you have Rayleigh scattering, I explained that briefly, where you have now this non-resonant excitation, and now look for the elastic scattering, different to Raman, where you end in the same state where you started from. And so if you look at this equation where the Rayleigh signal is now linked to the density n over volume, the number of molecules in your control volume, it is dependent on the laser intensity, clear? It's a linear technique, it's exponential 1. It depends on the Rayleigh cross-section, and you have to calibrate it. And so if you know the Rayleigh cross-section, if sigma ray is known, and you know the laser intensity, then you can directly say you have a direct measure of the local density, which then we can turn into the temperature via the equation of state if you know the pressure. Let's say you have a low number flow, you have one pressure sensor somewhere, and then with the calibration measurement that can be directly used to measure the temperature. I think that is a direct and possible way. However, the restriction is you have to know the Rayleigh cross-section. And that is the problem. The Rayleigh cross-section can be estimated with this formula, where you have here the wavelength of the excitation that is known, okay, and the refractive index of the gas species. And that is different from O2 to N2 to CO2 to water and so on. And that makes that this Rayleigh cross-section is dependent on the chemical species I. And if you don't have the chemical composition, you have not an unknown sigma ray, an unknown cross-section. So to compensate for that, if you want still to use Rayleigh scattering to measure the temperature with an unknown gas composition, you can't do it. Because the Rayleigh cross-section is the mole fraction weighted sum of the cross-sections of each species, right? And so that if you know the mole fractions of the species in your probe volume, if you would know these mole fractions with the known cross-sections, you can calculate an effective cross-section, put it in, and you're fine again. But the problem is you have to know the gas composition. And to get the gas composition, that means you have to measure it, yeah, right? In flames, you don't know it. You have to measure it. And that's why it is combined with Raman scattering in practice. And that is well, I think famous Raman-Rayleigh spectroscopy, which is maybe the most useful technique when you want to get not only the temperature, but as well the species concentration, and thereby the thermochemical state. And as I said yesterday, there are only few labs worldwide doing that, because in practice it's really complicated to get a good signal to noise. But all what we know about finite rate chemistry effects in the, for example, Sandia flame D, you might have heard about that. That all comes from that kind of spectroscopy, yeah, Raman and Rayleigh combined. And so typically it is done in such a way that you measure multiscalars with Raman, as I've pointed out here. I've shown that I think already the principle of Raman spectroscopy to get species concentrations is to exploit that you shine in the same laser in the same probe volume, but because the different molecules do have different Raman resonances with different energy separations, the Stokes scattered light does have different frequencies or wavelengths. And if you now disperse that, you have shown that view graph already, you can see now after load, with a low dispersion, typically a 30 centimeter spectrometer, you see the different species in your flame, and that can be now simultaneously with the Rayleigh scattering can be used in an iterative procedure, I'll explain in a second, to deduce the thermochemical state. So temperature plus main species concentration. And this information about main species concentration, again, is needed to be put in this mole fraction to calculate the effective cross-section. Okay? That is the idea. And that is now done in the following way, because the Raman signal to get the concentration, the number density of this molecule, depends on the Raman cross-section. And the problem here is the Raman cross-section itself is temperature dependent. And so, well, we don't have the temperature. However, the other equation for Rayleigh shows you here, gives rise for the density, but the cross-section here is dependent on the species concentration. And neither of them you know initially. And so the simple way to do it, you just start an iteration. You say the temperature is 1,000 Kelvin, okay? You can take as well 900 or 1,500, doesn't matter. Let's take 1,000 Kelvin. With the 1,000 Kelvin assumption, you calculate the Raman cross-sections. With this known, you take the measured Raman intensity for each species. I go back from all these peaks, you integrate them, you know them, you deduce the concentration of each species, and then you put this species in here, you calculate the effective cross-section. With that, you get the density. With the equation of state, you get the temperature, and then you have a different temperature from that you started with, and after the first iteration, you repeat everything, and then after a couple of iterations, you converge. And that must be independent of your initial choice, of course, but that works typically within 3 or 4 iterations. You got it? Okay. Yes?
Does the Rayleigh cross-section depend on temperature?
No, that's the good thing. It is, if you go from 300 to 2,000 Kelvin for, let's say, N2, the cross-section changed by less than 1%. Otherwise, we would have been lost. Yeah. Knowing these things here, this temperature dependency here is not a trivial task. Yeah. So there, just as a side note, we use here information from people from quantum chemistry, and there are single groups working, for example, only on water. Yeah, water vapor, understanding the cross-section of a Raman of the water molecule, and doing that for 30 years. Yeah, and so that is the kind of information we need and we rely on, and we just exploit it for these purposes. Well, let's have now some examples to make this more interesting. Maybe later today I will talk about some flame wall interactions. I would like to start with some Raman Rayleigh measurements and thermochemical state measurements in a premixed flame, and then refer to the measurements in the IC engine. So you have seen that again. This is our swirling premixed flame that we have studied for many years, and I refer here to one test case where we have performed Raman Rayleigh measurements in different heights. You see a cross-section of the nozzle. You see the not very spectacular statistically stationary flame. And you see here at this height there has been measured line-wise Raman spectra. And maybe more information about that has been done. We do have a laser cluster. Maybe just a side note here. As I said, the Raman cross-section is very low. You need many photons to get a reasonable signal. And for that you need high-power lasers. And so in that experiment we have used 4 lasers which were fired sequentially. But if you would focus an 8 nanosecond, 500 millijoule laser pulse at 532 into your flame, yeah, you would create a plasma. You cannot do it. And that's why we have to stretch the pulse in a delay line, or in multiple delay lines. And that's not nice, but that is something how you can make from one pulse many pulses, and what you gain is that each pulse does have lower energy, and thereby you have lower intensity if you focus it, and thereby you can avoid this optical breakdown in the probe volume. Okay, let's given that is given, then we have a 1D probe volume that is nowadays better. We were able to go down to 150 microns beam waste, and the length is in the order of 4 millimeters. Then you collect as many Raman-Rayleigh photons as possible. So this is a custom designed lens. It's a huge lens, yeah, because you want to get as many photons as possible, yeah. This is an F number of 2. Then you have at the exit, it's an achromatic lens. You bring it onto a beam splitter. This is a dichroic beam splitter where you cut off the Rayleigh photons going here, 532 nanometers, goes this way along a line. And the remaining, the Raman photons are spectrally dispersed in this spectrometer. Where you then have as well, one dimension of the spectrometer is space and the other direction is wavelength to get for each local position a spectrum. And now here is a spectrum given for one location, and you see here a spectral fit. Based on all this quantum mechanical information, we are able to fit spectra to this noisy experiments and deduce here the thermochemical state. And this gives you some idea, although we tried as good as possible, all these wrinkles here, this is scattering, this is noise. And that is something it goes too far how to do it better. We don't do it with a spectral fit anymore to reduce the noise. We do it differently, but maybe that is too much of detail. Then you can, along the probe volume, get it discretized. For example, in the Raman direct, for the Raman scattering in the order of 300 microns, because Rayleigh is much more intense. You can go below 100 microns, such that you have a resolution which is kind of good to resolve even flame fronts in premixed flames. And then you find sometimes profiles like that, 2000 or nearly adiabatic flame temperatures along the probe volume. You're inside the flame, you're around 300 Kelvin, you're outside the flame. Sometimes your probe volume intersects with the flame front and you find, oh, it's quasi-laminar flame fronts, and that refers back to the Borghi diagram. It is in the regime where you expect as well flame-like behavior. But however, due to turbulence, you sometimes find as well things like that. And that might be as well that you have wrinkled flames and you intersect with your volume those wrinkles like that. Hot, cold, hot, or the other way around, whatever. That is the effect of turbulence. And maybe they can squeeze out now information. What can you learn from that? You see here to the left the temperature profile, the mean, and you see here the variance. And this is just, 0 is just above the bluff body. Here's the annular slot, and here's the outer flange. And you see here, for example, that you have cooling. This is measured at 10 millimeters above the bluff body. You see here reduced temperatures because you have a recirculation zone bringing the hot fluid back, and then it's cooled at the bluff body, and this is due to the cooling. If you go to this region over here, where you see there is the temperature gradient, there you have fluctuations because your flame is not stable. You have intermittency. That's why you have as well higher fluctuation values. And it's here as well where you find high CO values, clearly, because the reaction is not complete. Then you go here into the annular jet. You find there's no reaction. Temperatures are low, but you're still in the part where you have pre-mixed gases coming out. And you see that the equivalence ratio goes only to 0 over here, where you have the outer mixing layer. But there's no reaction. That means at this height, it's a purely pre-mixed flame, yeah, because it burns in a constant equivalence ratio. And then if you go for higher heights, well, as expected, you have now temperatures that are getting, the mean temperature distribution is getting decreased in its gradient because of course, the intermittency, the flame brush goes up. That's why you have here this wider distribution of temperatures. And as well, now you find, for example, here at 60 millimeters, where you have the mean temperature like this, the mean equivalence ratio like that. At this location, the flame is not purely premixed. It will be diluted from secondary air, and thereby you will have as well stratified flames at higher positions. Okay? Maybe we go not through every detail. Maybe more interesting is to look at these scatter plots. So that's the real benefit of Raman and Rayleigh. Each of the scatter, and I have shown only 1/10 of them. Now you can plot something like CH4 or CO, whatever you're interested in, the equivalence ratio, against your progress variable, the temperature. And if you do so, You can see nicely correlations where you have, for example, here in this region, where you have no CH4, but equivalence ratio of 0.83 and high temperatures. This is fully burned. Yeah? This is fully unburned. You have CH4 to a large extent, low temperatures, equivalence ratio of 0.83. So this is premixed, but not yet burned. Anything in between is on the pathway of reaction. It's in the flame front measured. You have an idea why it is more probable to measure burned or unburned, why it's so less probable to measure something in between? Any idea? Well, short wavelength? Short length? Well, short lifetime is, yeah, you can say that. Pardon? Density difference? No, that is not the case. The residence time, yeah. You have a flame front which is maybe only 500 microns, yeah, and you have something like a 6 millimeter long probe volume, and then you have simply less because of the lifetime of those intermediate states. It is less probable to capture them. Yeah, exactly. That's it. And you have here this C state over here. You have no methane, equivalence ratio of 0. You're cold. This is the surrounding air. And then this obviously is mixing between air, secondary air, and premixed gases coming from the annular slot. Yeah, this is this mixing line over here. And then you can, this is shown secondary air dilution, reaction without dilution, and so on. And then it's interesting, of course, to refer to where it's measured primarily. This is now color-coded. This is the internal reaction zone. This is primarily reacted cases. You have here in the inner mixing layer the central annular jet. This is green and blue. That is either not reacted or something in between. You have here the outer mixing layer. This is not reacting at this height. You have just mixing, and you finally have this green spot over here. That is the co-flow. This is the secondary air. And thereby, you have now a completely different view than just looking at mean and variances. Yeah, you can use in the state space representation. You can much better understand what's going on. And it's now very interesting to compare 10 millimeters to 30 millimeters, whereas we have had mixing without reaction and then reaction without mixing. Now we have at 30 millimeters everything in between. Yeah, and that can be due to mixing here or due to local extinction. Okay, that is not clear. That cannot be distinguished with this data, but it is very rich in its information. And that must be somehow covered by your combustion model. Yeah, and that is something that is still ongoing, and it's not finalized, and is of course very important if you want to understand pollutant formations in such flames. All right, and so maybe the conclusions. Not so important to go through all of that. I hopefully made clear that this kind of experiment is of much more than just visualization and velocity measurements. Now you have really thermal-chemical states accessed, and you have turbulence chemistry interaction quantified by this way. And thermometry is the base of that, but extended to chemical species measurements. Because time is marching, maybe I go, unless you have questions. We should always have time for questions. Okay, then we go on and have a look into the gas temperature measurements in IC engines. For obvious reasons, that is very important to have that, and maybe I refer back to the question. Of course, the technique I'm referring to is now again the Toluene LIF we discussed briefly. It is, for example, very important to understand autoignition. Yeah, if you go for HCCI engines and want to understand what's going on there, then you would like to have a very accurate and precise measurement of the gases during compression. Yeah? That is something where you need techniques to that give information about it. And maybe another example, and not go discuss all of them, is it would be great if you would have a 2D temperature measurements in the thermal boundary layer to get access to heat losses. And that is as well something close to walls, measuring precisely, accurately temperature profiles is a very challenging task. And so once again, you've seen that. I don't have to repeat all the details. Just to remind you, it's a very different technique again. To Rayleigh-Raman, it is this temperature-dependent emission, where we typically take here now the ratio of these two wavelength regions, and then are able to measure temperature stratification. And that has been done before we did it as well from people like John Deck, but at low repetition rates, just one shot per cycle. And we try to extend that for high-speed measurements and combine that with PIV to get as well information about the flow field and the transport there. And this again is what you have seen, this view graph, just to remind you how it was done. Once again, the laser came 266 nanometers, 6 kilohertz, 1 millijoule per pulse, was intersecting this central tumble plane just below the exhaust valve, and then we were viewing with these two cameras through this beam splitter over here, the blue channel and the red channel, and took the ratio. Yeah, and this ratio, once again, we discussed that, is shown here. And so now I would like to discuss some more results. So first of all, the region was restricted to a certain fraction because simply we didn't have sufficient laser energy to illuminate the whole cylinder. So this again was a compromise, have a smaller field of view, and thereby have a better signal to noise. The cylinder head temperature was set to 333 Kelvin, similarly to the intake flow. So this was a motored engine filled or operated with nitrogen and seeded with toluene. And yeah. Well, we then did some post-processing. So the images were filtered, they were binned, and the spatial resolution in the end per pixel was 0.08 millimeter per pixel, 80 microns. But of course, by this operation, it was decreased. And so maybe the spatial resolution in plane was in the order, I'm not sure anymore, I have to look that up, maybe in the order of 200 or 300 microns. And then maybe it's important now to come to the calibration, because in the previous things, I haven't discussed that. I should make this more clearly here. As I said, the technique needs a calibration. And well, we have now in motored operation the opportunity to measure as well the pressure and refer now, based on the pressure trace, we can calculate, based on a polytropic assumption, the temperature. And at the same time, over crank angle, you see here the temperature deduced from the pressure measurement over the crank angle. At the same time, we do have here our lift signal ratios. Yeah? And you see with that, we are able to refer, this is a calibration curve, and therefore we are able to have now, here's a detail about pressure and polytropic temperature, to get a calibration or a correlation between the lift ratio, which is shown here, and the temperature here. And now the question is, where does this lift ratio comes from? We have restricted ourselves to a region here in the center where we are far from walls. Yeah? Such that for all crank angles we have looked at, we assume, we don't know, but we assume that this central region is not affected by strong heat losses to the wall. And because of that, we can say this is something which is undisturbed by any heat losses to the wall during the compression stroke. We have averaged over this control volume to get a higher signal to noise, and we ended up, after taking this lift ratio, averaged over that with this curve over here. Yeah? And having simultaneously the temperature from the pressure trace over there with a certain variation, we can say, we can deduce the precision at room temperature. We are around 5 plus minus 5 Kelvin, 2%. At higher temperatures, at 540, we are around 5%, 5 to 6%. That is the kind of limitation we have with this high speed and this thermometry based on the ratio. Okay. If you, of course, would decrease your resolution and go, let's say, for a larger pixel binning, you get a higher signal to noise, and you can get a better precision at this higher temperatures. This again shows you have a compromise between spatial resolution and precision, yeah, in these techniques. Okay. So what you see here now is during compression, nothing happens. Yeah, you have here crank angles shown 300, 320, 340, 360. Not every crank angle is shown. And you see here the color-coded temperature. At the beginning of the compression, it is colder. Towards the end of compression, it is hotter in the order of 530 Kelvin. Not very impressive. Yeah, well, the compression ratio is as it is. It is now maybe interesting to see what happens in the expansion stroke. In the expansion stroke here, 390, 410 nanometers, you see, of course, everything is getting cooler. The piston is going down. But I would like to refer here to this region over there. You have significant cooler portions of air, of nitrogen in this region close to the cylinder liner. And of course, you can now look at PDFs. That's one way to look at this data statistically. Again, during compression, that is a well-behaved PDF. Okay, it has a certain variation. Part of that is the precision limitation you have. However, if you go to the expansion, you find, take the 410 as an example, you find a very different distribution. And this part of the PDF, this cold part, that refers here to that location over here. Do you have any idea why that is colder in this location? Heat loss, yeah, but this could be as well here at the cylinder head. Why is it here and not at the cylinder head? Well, we come now to show that for a good reason. This is a huge limitation of the optical engine we have because of the crevices. Well, let's have a closer look into that. First of all, in the compression stroke, we can nicely fit a Gaussian. Everything is fine, okay. Here, at the expansion, we can use this part of the PDF to fit as well a Gaussian. And then we have remaining parts of the PDF, and by subtraction, you see the blue part over here. If you now take a threshold value, this is set here at this location where the PDF has reached a certain threshold or is below a certain threshold. We take only those portions and identify this line is somewhere, or this PDF, this part of the PDF comes from this area. This is just what I said is now made quantitatively. And now you can as well see, actually this is not only in this one stroke I've shown, but statistically you see here now the probability of the occurrence of the cold portions at 410 Kelvin. This is really at these locations over here. Yeah, it is stronger here than, for example, here, although there's as well a wall. And the reason is, and that's now good to have some velocity information, this actually is outgassing of the crevices. And I have a video over here. We concentrate now on this area over there. And if you look to the right-hand side, you see overlay to the temperature field, the velocity field. And you see there is actually over the crank angles, maybe I should repeat it. There is a flow coming out of the crevices, which is cold, because in the crevices, of course, you have the piston and the cylinder liner. Everything is much colder there, and when the piston goes down, this crevice is outgassing, cools that portion, right? And this crevices volume in these optical engines are rather large, and that means in the late part of your combustion, it will be very different to a real engine where the outgassing is much less, okay? Say it again. They are showing, yeah, this is, well, they're showing down to the left, right? Yeah.
But the crevices
will be here, but the crevices outgassing is here. It comes out, and then it's transported to the left. Yeah? Maybe once again. It's doing that automatically. Great. Okay. All right. So combining techniques, as shown in this example, can be as well very beneficial to have a better understanding what's going on. And in principle, we do have now a technique to measure thermal stratifications as well in different environments and not in homogeneously compressed gases. When you have, for example, now spray going in, you can measure stratification due to evaporation cooling. I don't show that. We have done that. It's in principle now possible with a limited precision. However, that can give some idea as well about hotspots and so on. And so, as well, I think useful data for the future to be compared with numerical simulations. So we have 10 minutes left. Maybe before we go to the next topic, are there any questions regarding that example? Yes, please. The PIV and LF was quasi-simultaneously. There was always a certain delay between those, which is in the order of, let's say, 100 nanoseconds or something like that. It is fluid mechanically simultaneously, yes. Yes. Okay, yes. Why we do two color instead of one color? Okay, a two line, or, yeah, okay. You can...
One line, two color selection rather than...
Two line, one color. Yeah, actually, for the two color excitation, you need as well a second laser, which needs to be perfectly overlaid. And to experience it from other projects, that is always not easy to achieve, especially with UV lasers. And then you have, that comes along then with the fact you have to correct for each laser shot. And if you want to do that high speed, it's a much larger effort. Yeah. Maybe for the future. You have now the equipment, you can try. All right. Let's switch gears. Let's take the remaining 5 to 10 minutes to discuss something completely different. We have discussed so far gas phase temperature measurements. That's very important. But if you go now to real combustors, you have to have an idea about wall temperature measurements as well, about wall temperature. And to have something like thermal boundary conditions, get information about heat losses, to have two prominent examples why it's useful to do so. And phosphorus thermometry has been developed over the last, I would say, 10, 15 years to become a very robust tool to do so. And phosphorus thermometry has been reported in 3 review articles. The most recent one we published in PEX 2013. And I would like to refer to a work that we have published as well 2 years ago in the Proceedings of the Combustion Institute to give you some idea about pros and cons for the different ways you can do it. So first of all, I will discuss the experimental setup and briefly the data evaluation, and then I will stress a bit more on the precision and accuracy on the different methods that can be applied. So first of all, about the measurement principle. The measurement principle is based on exploiting ceramic materials. Ceramic materials that are doped either with transition metals or rare earth metals. And those ceramics are used to at least partly coat the surface you want to investigate. Yeah? But be careful. If you have a ceramic and it's maybe only 10 microns thick, it is an insulation layer. Yeah? And so this is not non-intrusive. At least you can say it's semi-intrusive. And if you do have a strong temporal variation, intermittency, then that might have a huge impact on what you're doing. And so be careful. And so let's say we have this thermographic phosphorus selected. Then we have a UV excitation of the phosphorescence. And then we can do different things. Either we exploit the fact that this thermographic phosphorus have a temporally dependent phosphorescence luminosity property, or that they change their spectrum with temperature. So these are the two main differences. And those are highlighted here. What I mean, you have here the phosphorescence intensity of a phosphor which is not specified. This was magnesium fluoride, whatever, with manganese doped. And here you have time. The laser pulse in this scale is very, very short. So it's like a delta pulse. Yeah? So you excite it, and then you observe the phosphorescence. And the phosphorescence at different temperatures, you see different decay behaviors. It's maybe not perfectly mono-exponential. Maybe here you can assume it's mono-exponential, not here. If you now fit a curve, maybe in the later part, to that, you get a decay constant, and the idea is the decay constant directly decodes the temperature. All right? After calibration. That's one possibility. The other possibility is spectrally resolved measurements. You see now here spectra of a phosphor for different temperatures, and you see that here this phosphor exhibits two bands at these two wavelengths, red and more blue, and the intensity of these relative intensities is changing. So this bluer part here is changing drastically, while the redder part is changing less drastically and in the opposite direction. If you take again, measure a ratio of fluorescence taken, or phosphorescence taken at these two bands, take the ratio, you can make a temperature dependency out of that. And this is now even more specified, and maybe that's the last graph for this morning session. You can go time resolved or time integrated. If we go time resolved, the first option is in the time domain, as just shown, measure the decay time, shown schematically once again. This is after a very short excitation, the decay, and you fit something like this equation, mono-exponential to that, and all you do is you determine this decay time. And the decay time is a direct function of the temperature. People have shown as well that if you have a high, for some phosphorus, after excitation, the phosphorescence needs some time to develop. And here, the rise time can be equally fitted such that you have, instead of, go back, the decay time, D, you have a rise time, tau R. That is well temperature sensitive. But this is only for very few phosphorus, and it's not used in practice. You can use it in the frequency domain. You can make an excitation which is not pulse, but CW, but you modulate it, amplitude modulation. And because of the transfer function based on this decay, you can now determine the phase shift between the excitation and your phosphorescence, and this phase shift is as well directly connected to the decay time, and thereby is a function of temperature. Or you go into the time integrated branch and either do it in the single spectral band, you just take your phosphorescence from the beginning to a certain threshold value and just integrate it. Shouldn't do it. But whenever you have any a change in the intensity because the laser fluctuates, because your window through which you observe is getting fogged or whatever, you have a different intensity, you think it's a different temperature, you're lost. That's why it's not a good thing. A line shift could be a better option. Some phosphors show that, but the line shift is not very strong. You need a high spectral dispersion, so it's maybe not as good as well. The better thing in the time integrated branch is to use the ratio. As we have seen, some of these phosphors have bands at different wavelengths, and those intensities change with temperature such that the ratio is as well a function of temperature. And if now the laser intensity is changing because of the ratio, that cancels. All right? And so the most popular approaches are the decay time or the ratio after a two-line detection. And so this is what I would like to compare in the following a bit closer and take this as an example that especially this ratio method is more prone to systematic errors than the other technique. Okay? All right. With this, I would like to thank you for your attention.